Okay, so this video is being recorded for physics, and we're looking at Module 9. And Module 9 deals with momentum. And I apologize, I'm not great with the stylus yet. Hopefully I will get better with practice. So when we think about momentum, you can think about whether you would prefer to be in a car accident with a small car that is traveling rapidly, traveling at a high rate, a small car or a large truck if they're both traveling at the same velocity. Or you can think about traveling in a small car or being hit by a small car that is traveling either at a slow speed or a fast speed or fast velocity. And we would all agree that we would prefer to be in a collision with a smaller car compared to a large truck, and we would prefer to be in a collision that involved a lower velocity compared to a larger velocity. So those thinking about those questions gets us then to the question of momentum. So first of all, momentum is a vector quantity. So when we are talking about momentum, we need to make sure that we indicate direction, and I'll talk about a little bit more about that in just a moment. And we usually define momentum. It's easiest to define it mathematically. So momentum, which we use the lowercase p to, is equal to mass times velocity. So a couple things I want to point out to you. First of all, as we know that velocity is a vector quantity, so it has direction, and we know that mass is a scalar quantity, so obviously it doesn't have direction connected to it. However, when you multiply a scalar quantity times a vector quantity, the direction of the vector there's no change in direction that occurs. So momentum then will be in the same direction as the velocity. So momentum and velocity will have the same direction. And that'll happen anytime you multiply a vector quantity times a scalar quantity. You won't get a change in the direction. It will be the same. Okay, let's talk about units. So if momentum, that was bad. So if momentum is equal to mass times velocity, we know that the units for mass are kilograms, and the units for velocity are meters per second. So the units for momentum are a kilogram meter per second. And there's no other name for that, so we don't, previously we've seen that kilogram meters per second squared is a Newton, or we saw that there's a separate certain units are called watts. We just call this just stays as kilogram meters per second. So the units for momentum are kilogram meters over seconds. When we are designating directions for momentum, sometimes it can just be directions like we can say north, south, northwest, etc. Or we could give the direction as a certain angle. So we might say that it's 45 degrees or 58 degrees, etc. And then in other cases, usually the sign, the positive or negative sign, will tell us the direction. So generally, if something is moving to the right, or if it is moving vertically upward, then we would signify that by a positive number. And if something is moving to the left, or if it's moving in a vertical direction and moving down, then that would be a negative direction. So this is the convention for directions if we're not being more specific with the directions, either by giving an angle or by giving directions like north, south, east, and west, etc. Okay, so now take a look in your, if you want to take a look in your textbook, we'll run through a few simple problems relating to this. So let's start with example 9.1 on page 288. And I'll read that and I'll write up the information that we are given as we do that. So example 9.1 on page 288, we are told that we have a 345 kilogram car, and we are told that its velocity is 19.1 meters per second, and it is traveling southwest. And then we're just simply asked, what is its momentum? So momentum is equal to mass times velocity. So it will just be 345 kilograms times 19.1 meters per second. So the momentum, would be 659,000 kilogram meters per second. Actually, let's see, I got too many zeros there. Let's get rid of these. And we could leave our answer like that, or we could say that it is 6.59 times 10 cubed kilogram meters per second. And we need to give a direction, so the momentum also would be in a southwesterly direction. Okay, now while I'm erasing this, you could take a look at the on your own problem just below that question. So on your own 9.1. So on your own 9.1. Okay, let's write down what we're given. We're given that it's a 35 Newton rock, and it rolls down a hill And at the bottom of the hill, it is rolling horizontally with a velocity of negative 13.2 meters per second. Okay, so this velocity is negative because remember, if something is going vertically in a downward direction, we signify it with a negative direction. Okay, so the first thing that you should notice is that we are given a weight and not a mass. So the first thing we would need to do is convert this weight into a mass. So weight is equal to mass times gravity. So weight divided by gravity will give us the mass. So the weight was 35 newtons, which is kilogram meters per second squared. And we will divide that by gravity, which is 9.8 meters per second squared. So the second squareds will cancel, the meters will cancel, we'll be left with kilograms. So that the mass is 3.6 kilograms. Okay, so then with that information, then we can, now that we have the mass and we were given the velocity here, we can go ahead and plug those numbers into our momentum equation. So P is equal to mass times velocity. So P is equal to 3.6 kilograms times negative 13.2 meters per second. So that P will equal negative 48 kilogram meters per second. And the negative sign is here simply to indicate that momentum will be in the same direction as the velocity, and we can have two significant figures, so that's why we have the negative 48 kilogram meters per second. Okay, for the next topic of discussion then is something that is called impulse. And when you think about impulse, think about throwing something against a window. If you make a ball out of a piece of paper and throw it against a window, the window probably is not going to break. But if you threw a baseball with the same velocity as the paper ball, if you throw that against the window will most likely break as long as the velocity is large enough. So what's the difference between the two? Well, first of all, you would say that obviously their masses are different. The baseball has a larger mass than the paper ball, and therefore its momentum is greater. But then we can also think about Newton's second law. And remember that Newton's second law, we expressed it mathematically as force is equal to mass times acceleration. So when an object hits a window, the window is, in order to stop that object, the window is going to change the object's velocity. And when you get a change in velocity, what is a change in velocity? A change in velocity is acceleration. So Newton's second law tells us then that in that situation there is going to be, because there's a change in direction, there's going to be a change in acceleration. Okay, so then Newton's third law tells us that for every time a force is applied, there's going to be an equal and opposite force. And in the case of something striking a window, the equal and opposite force would be the force, or the window will provide a force on the ball or the piece of paper, the wad of paper, and then also the ball or the piece of paper is going to provide a force on an equal and opposite force on the window. So that force, if you remember that acceleration is defined as the change in velocity, change in velocity over a change in time, so change in velocity divided by time. Then if we substitute this equation for the acceleration here, then we would have that force is equal to mass times delta V over delta T. So now let's just distribute the mass to both. Oh, and change in velocity is, so this is going to be mass times Vf minus Vi over delta T, because that's delta V is final velocity minus initial velocity. Okay, so then if we distribute this mass to both sides, then we get that the force is equal to the mass times Vf minus the mass times Vi divided by the change in time, divided by delta T. And what's this up here? This is mass times velocity. Mass times velocity, that's momentum. So Pf minus Pi divided by delta T equals F. Because this and this represent momentum values. So don't worry if you didn't follow all that derivation, but the bottom line is that if we apply Newton's second law and Newton's third law, then we learn that the change in momentum divided by the change in time is equal to force. So this is just another way of expressing Newton's second law. And in fact, when Newton first developed his second law, this is the way it was expressed. It was expressed like this. And then it was sometime later that this derivation of Newton's law was expressed. So what this equation tells us is that in order to change an object's momentum, you have to do what? You have to supply a force. You have to apply a force, and when you apply a force, you're going to get a change in that object's momentum. So if we look and we think about why throwing a piece of paper at a window won't break the glass, but a baseball will. Since the baseball has larger mass, its momentum is larger. So if momentum is larger, that means that the window is going to need to provide a greater force because of this greater momentum. And when the window provides that greater force with a baseball compared to a wadded up piece of paper, then that greater force will cause the window to break compared to if it's just a paper wad. So both Newton's law will apply in both situations. It will apply to the piece of paper wadded up, but also apply to the baseball. But because the baseball has a greater mass, then it's going to have a greater momentum. And so Newton's third law tells us that the ball will provide a force, will supply a force to the window. The window will provide an equal and opposite force, and because that force is going to be greater with a baseball compared to a wadded up piece of paper, then the window would break, and it most likely will not break if it's just a wadded up piece of paper. So we can also, so if we say that force is equal to the change in momentum divided by the change in time, well, we can rearrange that equation and say that the change in momentum is equal to force times the change in time. So, and this quantity here is called impulse. So the force times the change in time is called impulse, or it's called a change in momentum. So how does this concept apply in real life situations? So let's say we have a baseball player, and the baseball player is going to hit a baseball with a bat. When the bat hits the ball, it's going to exert a force on the ball, and it's going to stay, the bat will stay in contact with the ball for a period of time. So the force that is applied and the amount of time that the bat stays in contact with the ball will cause an impulse on the bat. And that impulse will stop the ball from traveling toward the batter, and it will cause the ball to travel in the opposite direction. So how can a batter increase the velocity at which he hits the ball? Because the greater the velocity, the farther the ball is going to travel. So one way that, so two things can be done to increase the velocity of the ball so that the ball will travel further. Well, one is you can increase the force that you apply. If you increase the force, that's going to increase the velocity. And if we increase the velocity, that's going to mean that the ball will travel farther. Well, then what is the other thing? The other thing that you can do is to increase the time that the bat stays in contact with the ball. So if you increase the time at which the ball stays in contact with the bat, you're also going to increase your impulse, and that will lead to a bigger change in momentum, and the ball will go farther. So how do we increase the amount of time that the ball stays in contact with the bat? And the answer to that is by, if all of you who have played really any kind of sport were probably told at some point to follow through. So if you swing a baseball bat, you don't stop the bat as soon as you make contact with the ball. You keep the bat moving so that you can increase the amount of time that the ball is in contact with the bat. Same thing is true if you're playing tennis. When the tennis racket makes contact with the tennis ball, you don't stop the racket, but you follow through, because by increasing the amount of time that the ball stays in contact with the strings of the racket, you are increasing the change in momentum, and that change in momentum will result in a greater velocity of the ball. Hockey players, same thing. Golf swing, any of those follow through activities will improve your skill at that sport. And in something like baseball, the really good batters are those that are able to not only swing the bat with a big velocity, but also they are able to keep that bat in contact with the ball as long as possible. Imagine, if you will, with me, and we'll probably do this experiment later in the in May when we get together to do all of the labs. Imagine you have an egg, and you have a metal sheet, a metal actually, let's just say this. I guess in your book they say this is a board, so a wooden board. And then we have a sheet, so a cloth, some kind of cloth sheet. And we're going to throw this egg, we're going to throw an egg up in the air. We're going to throw that egg straight up in the air, and then we're going to allow it to fall down until it hits the board, and we'll do the same thing. We'll throw that egg, another egg, up to the same height, and we will allow that egg to fall down and hit the sheet. What's going to happen? Well, this one is going to most likely break and splatter raw egg everywhere, and this one probably will not break. And why is that? Well, if we assume that the egg was thrown up to the same height in each case, the impulse is going to be the same in both cases. But if we remember that delta P is equal to force times delta T, so the force with which the egg will hit the board will be the same in both cases. What's the difference then? Well, the difference is that when that egg lands on a sheet, because of the give in the sheet, that force is going to be spread out over a longer period of time, and therefore the egg won't break. So it's a concept of, it gets back to the concept of impulse. So the board delivered its impulse over a very short period of time, and the sheet supplies its impulse over a longer period of time, so that the force was smaller. In the case of the impulse is going to be the same, the force is going to be smaller because it gets spread out over a longer period of time. So the concept of impulse applies in sports situations, and we'll demonstrate its application with throwing eggs onto boards and sheets later in the semester. Okay, let's let's look at example 9.2 in your book, which is on page 292. Example 9.2. Okay, so let's start by writing up the equations that we have. Let's put them up in this corner. So we said that P is equal to mass times velocity, and we know that F is equal to delta P, a change in momentum divided by the change in time. And then the other equation that we said, if we just rearrange this, we can say that the change in momentum or impulse is equal to force times delta T. Okay, so keep those three equations in our minds, and let's look at example 9.2. And that example says, in order to get the necessary range on her drives, a golfer must hit the ball, and we're told that the mass of the ball is equal to 0.0459 kilograms. So she hits it off the tee with an initial velocity of 30.0 meters per second at a 45-degree angle. If the ball and the club are in contact with, if the ball and the club are in contact for 0.120 seconds, with what force must she hit the ball? Okay, so the first thing, so we're interested in finding out the force. So we need to calculate delta P, and we're given the time. So delta P is PF. So it's PF minus PI, the final minus the initial. So what would the initial momentum be? The initial momentum would be 0 because it's just sitting on the tee. So so this would be PF minus PI divided by delta T. So let's figure out what PF is. So PF, the final velocity, is going to be equal to the mass times the velocity. Final momentum will be equal to mass times velocity. So we get 0.0459 kilograms times the velocity, which was 30.0 meters per second. So that will give us the final momentum, and then we'll subtract that from that 0 because the initial momentum will be 0, and then we'll divide that by the time, which is 0.120 seconds. So this times this divided by this, we're going to come up with 11.5, and our units are kilogram meters, because this is meters per second. And when we divide by this seconds, that's going to put it up on the top. So it's kilogram meters per second squared. So it would be the seconds times seconds squared, and that is newtons. So 11.5 newtons would be the answer to example 9.2. Oh, and we would need to specify that it's at a 45-degree angle. So again, the direction will always be, direction for the force or the direction for momentum will always be in the same direction as the velocity, and in this case we were told that it's 45 degrees. Okay, then the second part of that example problem, still in example 9.2, tells us that a baseball player catches a 145-gram ball. Okay, well, first of all, I'm just going to go ahead and convert that to kilograms because we know that we need to have the mass in kilograms. So I'll go ahead and convert that to 0.145. And actually, I guess it's 1.450 to get, if I want to get the significant figures correct. So 1.1450 kilograms is the mass. And it is traveling at a speed of 22.1 meters per second. If the player can exert a force of 55 newtons, how long will it take to stop the ball? So we know that delta P is equal to P final minus P initial. And in this case, the ball is going to be thrown or hit. It doesn't really tell us, but what the final velocity in this case will be, or the final momentum will be 0 because the ball is going to stop. So in the end, when the ball is caught, it will have no velocity, and therefore it would have no final momentum. So then we just need to figure out what is the initial momentum. So Pi is going to be equal to the mass times the velocity, 22.1 meters per second. Okay, so now delta P would be equal to 0 minus this quantity, which ends up being negative 3.20, or it ends up being 0. It ends up being 3.20 kilogram meters per second. So 0 minus 3.20 kilogram meters per second is what delta P is. So delta P is equal to negative 3.20 kilogram meters per second. What does that negative mean? It just means that it's going to be, it just means that the change in momentum is going to be opposite the initial momentum because it stopped. So it was traveling one direction, and in order for it to stop, it's going to have to travel, the momentum will be in the opposite direction. Okay, so then we can go, now that we know delta P, we know that F is equal to delta P divided by delta T. And we want to know delta T. So delta T, we can rearrange this equation and get that delta T is equal to delta P divided by F. Okay, so I'm going to erase some of this stuff up here so that we have room to put that up there. Okay, so delta T is equal to delta P divided by F. And we already calculated that delta P was equal to negative 3.20 kilogram meters per second squared. And the force that we were given was 55 kilogram meters. Oh, this is kilogram meters per second for momentum. And this will be kilogram meters per second squared. And again, because the ball is going to stop, the force also will be in the opposite direction of the initial velocity. So both of these quantities will be negative, and a negative divided by a negative will give us a positive for time. So if we look at the units, kilograms and meters will cancel. One of these, this second will cancel, and we'll just be left with seconds. So that delta T is going to be equal to 0.058 seconds. So it will take 0.058 seconds for the player to stop the baseball when it is thrown. Okay, let's do the on your own 9.2 and 9.3 next. So on your own 9.2, let's read that a baseball whose mass is 145 grams, so I'm going to go ahead and change that to 0.145 kilograms, is thrown by a pitching machine with a speed of 45 meters per second. If the roller wheels of the pitching machine exert 43 newtons of force, that's F, so this is V, this is M, then how long did the baseball stay in contact with the roller wheels on the machine? So we know that P is equal to mass times velocity, and we know that the final P is going to be, the initial P, so PI is going to be 0 because it's just going to be sitting there stationary in the machine. So delta P would be PF minus PI, which is going to be 0. So let's first calculate the final velocity. So this will be final velocity is going to be equal to the mass, which is 0.145 kilograms, times the velocity, which is 45 meters per second. So the final momentum will be 6.5 kilogram meters per second. And then we know our other equation that we have is that force is equal to delta P divided by delta t. So the change in momentum, we'll subtract 0 from that. So the change in momentum is just going to be our 6.5. And so we can rearrange this and say that delta t is going to be equal to delta p divided by f. So delta t will be our change in momentum, which is 6.5 kilogram meters per second, and divided by our force, which was 43 newtons, which is kilogram meters over seconds squared. So again, kilogram meters will cancel, this seconds will cancel, we'll just be left with seconds. So that delta t will be equal to 0.15 seconds. And so both the force and the change in momentum were in the same direction as the velocity, because in this case the ball was moving from a stationary position in initial momentum of 0 to a larger momentum, in this case of 6.5 kilogram meters per second. Okay, so that was On Your Own 9.2. Let's go ahead and do On Your Own 9.3. Okay, so for On Your Own 9.3, we are given that the mass of a tennis ball is 56.7 grams, and I'm going to go ahead and convert that to kilograms, so I'm going to divide by 1,000. So it's going to be 0.0567 kilograms is going to be the mass. And we are told that it has a velocity of, it's traveling with a velocity of 23.1 meters per second. And then, so the ball is traveling toward the tennis player. The tennis player then takes her racket and hits the ball. And now the ball is going to travel in the opposite direction. So it's going to travel at negative 29.7 meters per second. If the ball and the racket were in contact for 0.21 seconds, then how much force did the tennis player exert? Okay, so now we have enough information. We know that the delta P is equal to PF, the final momentum, minus the initial momentum. And we have enough information to calculate both of those. So the final momentum would be the mass. So we'll do that one first, 0.0567 kilograms times the final velocity, which was negative 29.7 meters per second. So this is going to be equal to the final momentum, and that is going to be equal to negative 1.68 kilogram meters per second. And then we can do PI, and that is going to be equal to the same mass, the same mass of the ball. And it's initial velocity coming into the rocket was 23.1 meters per second. So that math is going to come out to 1.31 kilogram meters per second. Okay, so we have PF and we have PI, so that now delta P is going to be the final, which is negative 1.68 kilogram meters per second, minus 1.31 erase that a little bit up there, minus 1.31 kilogram meters per second. So negative 1.68 minus 1.31, then delta P is going to be equal to negative 2.99. And the units are kilogram meters per second. So let's erase that, give ourselves some more room. So I'll just put this back up again. Delta P we just determined was negative 2.99 kilogram meters per second. Okay, so then again we know that the force is equal to delta P divided by delta T. So the force will be equal to negative 2.99 kilogram meters over seconds divided by delta T, and we were given the time as 0.21 seconds. Okay, so your seconds are going to cancel. And no, I'm sorry. No, the seconds won't cancel. This will be seconds, and this will be seconds. And when you divide by seconds, you're going to multiply that. So the force will actually, this divided by this is going to equal negative 14.2. I guess we can just have two significant figures. So negative 14 kilogram meters over a second squared, which is a Newton. So the force will be negative 14 newtons. And again, what does the negative mean? It just means that the force that is applied is in the opposite direction of the initial velocity. So the initial velocity was given as 23.1 meters per second. The force required to get the ball going at its final velocity, which was negative 29.7 meters per second, would be negative 14 newtons. The force would be applied in the opposite direction of the initial velocity. Okay, we're going to cover one more section, and then I'll have you watch hopefully I can get a little video up for you to watch that relates to this. And the other section that we're going to cover is the conservation of momentum. conservation of momentum. If we state Newton's second law in terms of momentum, we can think about a system that has no external forces acting on it. So if you think about watching two objects that are moving, and there's nothing, so they're moving and they're going toward a collision course with each other, but there's no outside forces. So that would mean no friction, nothing's pushing it or pulling it. If there are really no forces acting on the objects, then we could say that zero, that's what force would be equal to. So F, we would say is 0 is equal to the change in momentum divided by the change in time. Well, then if we multiply both sides times delta t, they'll cancel over there, and this delta t times 0 would still be 0. So we would get that 0 is equal to the change in momentum. So this means that the total momentum of the system doesn't change. So even though two objects could collide with each other, their total momentums must be the same. And this is referred to as the law of conservation of momentum. And what the law of conservation of momentum says is that if the sum of the forces acting on a system is 0, then the total momentum of the system will not change. So if the sum of the forces acting on a system is 0, then the total momentum of the system will not change. Now, that might sound a little bit like the first law of thermodynamics, which says that energy cannot be created nor destroyed. But the big difference is that with the first law of thermodynamics, there are no exceptions. So it doesn't, in every situation, energy cannot be created nor destroyed. But the law of conservation of momentum states that if the sum of the forces working on a system is 0, then the total momentum will be conserved. So if you think about it, there really aren't too many systems where that will be the case, because friction is always a force that is acting on objects. Air resistance is usually acting on objects that are moving toward each other. And even if something is moving where there's very few molecules, there would still be some molecules that are rubbing against each other, and that would cause friction. So there aren't a lot of situations where the law of conservation of momentum really applies. However, there are situations in which friction is low enough that we can assume that it's negligible, and so then we can say that the law of conservation of momentum would apply. And one example would be that if something is moving on ice, there's going to be very little friction between the surfaces. And then also for most objects, if they're heavy enough and if they're moving at a reasonable speed, we could also ignore air resistance. So even though the law of conservation of momentum doesn't really apply very often in real life situations, we can do some problems if we assume that friction and air resistance are negligible in certain situations. So then when we start to think about whether the law of conservation of momentum applies in certain situations, then we need to ask ourselves, how do we know whether the forces acting on the system is zero? So the first thing that you have to do is you've got to define the system. And the objects within the system can be exerting forces on each other, but neither one of them can be, the sum of the forces from outside the system has to be equal to zero. So if we look at example 9.3, we have a tennis player hitting a tennis ball with her racket. Does the law of conservation of momentum apply in this situation? So the first thing we have to do is we have to define the system. And in this case, the system would be the tennis ball, and it would be the racket. So if we think about what will happen, the tennis ball is going to hit the racket, and then the racket's going to cause the ball to start traveling in the opposite direction. So since the woman is swinging the racket, the racket's going to have momentum in the direction of the swing, but the ball's momentum is going to be in the opposite direction. So because the woman in this example is supplying a force to the racket, that's an outside force, and therefore the sum of the forces acting on the system is not going to be equal to zero. And so the law of conservation of momentum does not apply in this situation. So the tennis ball and the racket themselves don't have any forces between them, but the woman is supplying an outside force, and therefore the law of conservation of momentum would not apply. Another example is a couple is performing an ice skating routine. The man stands still, and the woman leaps into his arms. Okay, so we have two skaters. So we have the man here, and he's standing still, and we have the woman here. I'll make her with a little skirty thing. And she is moving toward the man, and they're on ice, so this is ice, so we can say that there's, very little friction. So what's going to happen? The woman is moving toward the man. She's going to jump and land into his arms. Are there any outside forces acting on the system? Well, the system is the man and the woman. So the woman is exerting a force in order to be able to get off the ice, but she's part of the system, so that doesn't matter. But there's no outside forces acting on the system, and so the law of conservation of momentum would apply. So whatever momentum, since the man is standing still, whatever momentum the woman had before she is caught by the man, that momentum has to be conserved. So what will happen? In order to conserve that momentum, so now when the woman jumps into the man's arm, now their mass is much greater. And so the velocity, in order to keep the same momentum, so remember momentum is mass times velocity. Well, now their momentum is going to be much greater. So that means the velocity is going to go down so that the momentum will stay the same. And so the man and woman together will be moving at a lower velocity because of this greater mass, and they will also move in the direction of the woman's initial velocity. So they'll actually move. In this case, the man would be moving backwards, so actually, because they will move in the same direction as the woman's initial velocity. Example 9, I'm sorry, On Your Own 9.4 also discusses so On Your Own 9.4. Let's read that. An astronaut is floating in space near his ship. He has a ball in his hands and is essentially motionless. He suddenly throws the ball. Does the law of conservation of momentum apply to the astronaut and the ball? So any force that is exerted by a member of the system is irrelevant. So there's no gravity. And if he is floating in space, we would say that there are few molecules in the air, so any sort of friction is negligible. So the law of conservation of momentum does apply. So the system in this case would be the astronaut and the ball. And there are no, we just said there's no friction, there's no gravity, and therefore the law of conservation of momentum would apply. Okay, then if we look at the On Your Own 9.5, On Your Own 9.5 says a toy car is rolling along the floor. It suddenly crashes into the wall and comes to a complete halt. Does the law of conservation of momentum apply to the car and the wall? Okay, so now we have a car and it's moving toward a wall. And the car is moving with a certain velocity, but then it stops. So its final velocity is going to be equal to 0. And since we know that momentum is equal to mass times velocity, if the mass of the car is not going to change, the mass of the wall is not going to change. So this would tell us that the law of conservation of momentum does not apply, because if this becomes 0 and this stays the same, then momentum would definitely change. So the law of conservation of momentum does not apply. So then the question becomes, well, what was the outside force so that the car and the wall, what force was acting on it that, so the wall exerts a force on the car, but the wall exerts a force on the car, but it's part of the system. But then there must be some force acting on the wall, and so this wall is being supported by the ceiling, and it's also being supported by the floor. So those are outside forces. So even though the system was the car and the wall is experiencing some outside forces, and that means that the law of conservation of momentum will not apply. Okay, I would like to try to show you a video that helps to also illustrate the law of conservation of momentum. So I hope that you can see this video. This is a device that is called Newton's Cradle. And from this, you should be able to see that the law of conservation of momentum, because when one ball on Newton's cradle is pulled back and let fly, it will, when it makes contact with the remaining 4 balls, only the one on the end will move, because the momentum of the system needs to be conserved. So let's watch this video and see. Okay, so we'll stop there. I think you got the point, is that when one ball was pulled back and allowed to hit the other 4 balls that were hanging, only the ball on the end, the other end, moved. And that is so that the momentum could be conserved. When 2 balls were pulled back and allowed to hit the remaining 2 or 3 balls, then only the 2 balls on the other end would then move, so that the momentum could be conserved. Now you might think that you couldn't you also conserve momentum? So if you pull 2 balls back, if you pull 1 ball back, couldn't 2 balls move on the other end at half the velocity? Because we said that momentum is equal to mass times velocity. So if 2 balls moved, you would increase the mass, and couldn't you just have those 2 balls go at half of the velocity and you would still be able to maintain the momentum? And the answer to that is no. And the reason for that is that even though you might be conserving momentum that way, you would not be conserving energy. And we remember from the Newton's third law that energy cannot be created or destroyed. We have to also conserve energy. So let me remind you that kinetic energy is equal to 1/2 times the mass times the velocity squared. So if we took this and we kept the mass the same, and we took velocity divided by 2 for 2 different balls, then really what that ends up to be is that it ends up with equaling mass times velocity over 2 squared, and that is equal to 1/4 times mass times velocity squared. So in this case, you're going to be reducing the kinetic energy by a factor of 2. You're going to be cutting it in half. And so because energy cannot be created nor destroyed, you can't divide the velocity. You can't divide you can't say that the mass can be divided by 2 different balls and then just cut the velocity in half, because in that case, then you would not be conserving energy. So maybe you've seen those toys. Again, it's called Newton's cradle. Some people keep them on their desk, but it's an apparatus that is a great way to illustrate Newton's, or the law of conservation of momentum. Okay, I think we'll stop there for today, and we'll pick up on the rest of Module 9 next week.